All right, folks, welcome to our next workshop in this series. So today we're going to be doing theory of parallel computing. So this is going to be, it's a slightly adapted workshop from one that we've done previously. So we've had a workshop that previously encompassed both some theoretical ideas about parallel computing and some more practical ideas about parallel computing. So this one's going to mostly focus on some theoretical ideas. So we're going to cover the basics of what parallel computing is, and then move through some different ideas that will hopefully help you conceptualize this material and hopefully then give you the background to get into some more applications that we're going to cover next week. So just to start with this, we're starting to do these pre-workshop surveys. So if you wouldn't mind, I sent this out previously, but if you haven't done so yet, please try to fill out this survey. It should only take a moment. And that will help us collect some info on how these workshops are going and who's attending them and what we can do to improve them. So if you have just a moment to fill out this form, you can either click it on the slides or scan the QR code there, and that should be able to take you to the form and just fill that out. And just as a heads up, try not to submit a duplicate if you've already done so. Just doing it once is good. And so also, if you're watching on YouTube later on, so we're doing a live Zoom session right now, but if you're watching this recording later on, we still do want to hear from you. So just take a moment. You can pause the video and fill out this form. With that, let's get into the material. So here's an overview of what we're going to be covering today. So we're going to start with an overview, big picture. What is parallel computing? Why do we do it? Then give some theoretical background, just terminology, basic ideas. Going to cover some things like paradigms, taxonomy, scaling laws. And then towards the end of the session, we're going to get into some other concepts from parallel computing. So this is going to be kind of course, this is only one session. This could be an entire semester's worth of material on the theory of parallel computing. So we're just going to be able to show you a handful of different concepts, hopefully get you thinking about these types of things, show you what types of considerations exist. And, if you want to go deeper in this, you can, you now have more of the context and the basic ideas to be able to do that. So let's get into it. And if there are any questions that come up at any time, please feel free to drop them in the chat or feel free to just ask. Go ahead and unmute yourself and ask away. I'll be able to hear you. So yeah, let's get into it. So parallel computing, why do we do parallel computing? What exactly is parallel computing? So the idea here is that oftentimes when we're running these research computations, it's a quite large task. Big tasks are often composed of many smaller subtasks, and frequently, not always, but frequently, it doesn't matter the order in which they're completed. If you imagine, harvesting grain on this field, it doesn't matter whether I complete row 15 before I complete row 20. What matters is the amount of grain that you get at the end of it. And a lot of computational tasks are similar in that way. So it's usually possible to break down these things into smaller tasks. So some advantages of parallel computing is that if you have a particular project that you're working on, implementing parallelism might be able to decrease the time to your result, or it can increase the number of problems that can be solved using parallel computing. You can also increase the size of problems. So I can scale up my, if I'm running a simulation, now I can run it on a much larger scale than before, and I can introduce additional complexity to my model in order to accommodate real-world complexity. So that's an important advantage of parallel computing, especially in the research context, is that it accommodates complexity. So natural processes can be modeled with higher resolution simulations or models. So having more components, more types of interactions, and evolving these systems in a temporal sequence is often what's done in systems like galaxy formation or climate modeling or plate tectonics, anything. There's so many different types of fields that can take advantage of this form of modeling. And an additional example could be natural language processing models have billions of parameters. So it's maybe not quite a physical simulation type model, but it's still a model that it gains an advantage from additional complexity. So what exactly is parallel computing? Well, in order to answer that question, we first have to answer what is serial computing. So in a single processor computer, typically what happens is a problem is broken down into a sequence of instructions, and that sequence of instructions is fed into the processor sequentially, one at a time in the order that they have been divided into. So serial computing, pretty straightforward. The problem is broken into discrete series, of course, sequentially, and only one instruction executed in each time step. So parallel computing takes the problem and divides the problem into discrete parts that can be solved concurrently. So parts that are able to be solved at the same time. And then those parts are then further divided into serial computing domains. So you have instructions that are then completed sequentially. Instructions from each section execute simultaneously on different processors. So this is an important feature of it. You know, if I need the output of one computation for the next computation, that process might have to wait around for the other one to be complete. So this idea of independent processes is really important to parallel computing. And generally speaking, you need to employ some overall coordination method. You have all of these processors working on the same problem. If they need to share information between each other, you need to implement some type of, they call it a communication protocol. So just to put these pictures next to each other, serial computing, single stream of instructions fed into a single processor. Parallel computing, multiple streams of instructions fed into multiple processors. So this is big picture overview of the difference between serial and parallel computing. So it's also important to note that in this day and age, true serial computation is very rare. The majority of standalone computers are parallel from a hardware perspective. So there are multiple functional units, multiple execution units, multiple hardware threads. And here's just a list of different types of components of a CPU and data types that might be used in that CPU. So modern chips are typically quite complex and involve some degree of parallelization. And in the context of building research clusters, these types of systems can be built from relatively cheap commodity components. So the purpose of these is not to, you know, if you have a MacBook M1, the chip in there is likely much more advanced than the chip that you might find in the CPU of a parallel cluster, just because the more general purpose nature of the laptop requires a more complex type of CPU, whereas the research computing machine, the purpose here is to have as many as possible, not to have particularly complex CPUs. So that's the basic idea. So parallel computers here on the right, you see the Puma rack layout. Sorry, it's blocked a little bit, but you know, this is just a list of nodes and things that are in the Puma supercomputer here at U of A. So networks connect multiple standalone computers, also called nodes, to make larger parallel computer clusters. So that's what a supercomputer is. Each compute node is a multiprocessor parallel computer in and of itself, and those compute nodes are connected via a high-speed network. There are also some special purpose nodes, which are also multiprocessor in nature. So there's GPU nodes as well as high memory nodes. So each of these provide an additional resource that are not available on the standard nodes. So here's some terminology. So now we're going to just go over a few key words that are often used when talking about parallel computing. And we're going to do this just to make sure that we're all on the same page about what these terms mean, because sometimes there's a little bit of confusion as to what they are. So let's go through and try to clear that up a little bit. And as always, if there are any questions, feel free to let me know. So a node is an individual computer. Oftentimes the word node gets confused with a CPU. So in this case, a node is actually an individual computer capable of standalone functioning on its own. And the node contains a CPU chip, a central processing chip, on which there are multiple processors, right? So CPU, also called a socket or a processor, is a physical device mounted on the motherboard. Puma nodes have 2 CPUs. And a core is the component of a CPU that is capable of conducting independent work. So Puma CPUs have 48 cores. So if a CPU on Puma has 48 cores and there are 2 CPUs per node, that means each node has a total of 96 cores. If you are an experienced user of the HPC, you might note that I thought Puma had 94 cores. That's because 2 of those are reserved for the operating system and 94 are available for compute work by users. So this is the basics of the construction of a compute node that goes into a supercomputer. Again, node being an individual computer, CPU being a physical chip that is on there, and that chip can have a number of independent cores that are capable of conducting work, right? One complication here is in our task scheduler, some of these words get confused or sometimes they mean the same thing. In this case, CPU, according to Slurm, is the same thing as a core. So it's important to be aware of whether you're using a term in a hardware context or whether you're using a term in a software context. Oftentimes, the software context, the lines are a little bit blurred between what things are because a lot of those details don't matter to programmers, but from a hardware perspective, there's a little bit more specificity. So it's just important to be aware that there are those 2 different domains of terminology. All right, moving on. So a process is an instance of a program with access to its own memory, state, and file descriptors. So, if you're thinking about, I'm running a Python program, that Python program has initiated a process. Inside of that process, it has been allocated a certain amount of RAM, a certain amount of memory, right? A process state, as well as a certain regime of memory addresses that it has access to. And typically speaking, processes are independent. So if one process goes down, it shouldn't affect another process by default, unless it's specifically designed to do so for some reason. A task, on the other hand, is a logically discrete section of computational work. So a process might involve multiple tasks. A process might be parallelized, for instance. It might be able to run multiple tasks simultaneously, even though the process is considered one instance of a program. And then a thread is the highest level of code executed by a processor. So each process has at least one thread. Sometimes it might have multiple threads. And then threads are sort of an instruction level thing. And then tasks are more of a computational work level thing. I don't know if that distinction makes sense. I hope it does. So process versus task versus thread here. So process being a more higher level one, thread being a more lower level instance of, thread being a more lower level instance of a task, right? Yes, question?
Can you explain a little more how the relation between a thread and a code? I mean, it says it's the highest level of code. What's a lower level of code?
So a lower level of code, the question is, what's the relationship between code and thread? So when you think about your code, that's being passed to a compiler. The compiler is translating that into a set of instructions that get passed to the CPU. So a lower level could be considered that set of instructions. That's not something that the programmer typically looks at directly. That's something that gets generated by the compiler when the program, well, it depends on the nature of the program. But when the program is run, the compiler passes instructions to the CPU, right? On a very simple basis. There are many different ways that this can function, runtime compiling versus compile time. There's a lot of different ways that can happen. Okay. So moving on to some more pieces of terminology here. So NUMA refers to non-uniform memory access, and this is a particular type of architecture that you might see on a core. So it means that a global address space is shared by all cores, and memory is local to each processor, typically speaking. And then cache memory is a memory chip that is typically mounted much closer to the CPU, and that means that it's much faster, more expensive because it's a little bit more complicated to mount it in that way. We don't need to get too much into the details of the different types of cache memory and things like this. It's oftentimes not relevant unless you are writing low-level code, which that's not really our intention here. So let's talk about the types of computation that are available on HPC. So we talked about serial computation before. This is a computation that runs on one core, on one node. Sometimes it's called high throughput computing. This is, again, just breaking down one problem into a discrete series of tasks and running them sequentially. So you only need one core in order to do this. So one type of parallelism that's available on HPC is called shared memory parallelism, also called multi-threading. It's when a single process is run with multiple threads on multiple cores, typically on a single node. So remember, a node is one of these standalone computers. So you can think about all of these cores being run on a single one of these machines. So there is low-level coordination and threads having access to the same memory space. So the important aspect of this is that each of those threads has direct access to the same memory space on that chip. And this is to contrast with distributed memory, also called multi-node computing. So in this case, cores are allocated on multiple nodes. Typically, you would want to use as many cores as possible on a single node. There's not really an advantage. If I say, just for simplicity, I have a node that has 16 CPUs. If I want to run a program that has 16 CPUs, it would make much more sense to run that on a single node rather than running it, say, 8 cores on one node and 8 cores on another node. There's no advantage to this because there is an additional overhead of communication that needs to occur between those nodes in order to get those processors to work together. So when you're using distributed memory or multi-node parallelism, the idea here is that you'll be using multiple entire nodes. So on Puma, for example, I could use 2 whole nodes that each is allocated the 94 CPUs, and that would sort of maximize the amount of compute that I'm getting out of it while reducing the amount of communication overhead rather than splitting it amongst a higher number of nodes. So distributed memory, that idea here is that the threads on your work don't have access to the same memory space. So in order to coordinate their work, they need to communicate with each other. They need to say, hey, I finished doing this task. Here's my output. Send that to the processor that's on the other node so that it knows what's going on. So there's a much more complicated communication that needs to take place during distributed memory when compared to shared memory or multi-threading. So again, just to summarize, shared memory, single node, all processors have access to the same memory space. Distributed memory, multiple nodes, communication required in order to get those processors to work together because they don't have access to space.
Yeah, we're supposed to be there. We're supposed to be. It's news. Right. Hey, we worked.
I'm sorry, is there a question? Okay, if not, then we'll continue on with the parallel computing terminology. So just some more terms here that you might encounter. Massively parallel refers to workloads that use many hundreds or thousands of cores, typically multi-node types of jobs using many, many nodes, each with however many cores exist on that particular type of node. Embarrassingly parallel is a term used to refer to a task that has perfectly independent computations that will achieve ideal scaling. So in order to write an algorithm that achieves parallelization for this task, it's much simpler because the tasks in and of themselves are independent. So another term here, MPI, refers to message passing interface. This is a standard. It's not necessarily a code in and of itself, but it's more like a protocol, a set of rules that exists to define multi-node communication for distributed memory computing. There are a handful of different implementations of MPI. We're only going to talk very passingly about MPI today, and we'll talk a little bit more about it next week when we do the practical. Yes, question?
Why is it called embarrassingly parallel? Like,
Your guess is as good as mine.
yeah, that's a funny name.
It is a funny name. And some examples of implementations of MPI include OpenMPI, Intel MPI, MPitch, MVA pitch. So there's a handful of different implementations that are compatible with different types of software. So just important to be aware that MPI is not a code in and of itself, and that there are a variety of different codes that will implement this protocol. And on our U of A HPC clusters, we typically use OpenMPI mostly, and in some cases, Intel MPI. So we're going to talk a little bit about the basics of computer architecture so that we have a little bit of an idea of how these things are structured together. So the modern computer architecture comes from a mathematician, John von Neumann, who authored the general requirements for an electronic computer in 1945, and he proposed this model of a stored program computer. Previously, prior to this, computers did not store their programs. The programs were written out on punch cards or other physical media that were then fed into the computer, and then the programs were read from there. So the stored program computer represents a paradigm shift in computing where the program is now able to be kept inside of the memory of the computer rather than in some external thing. And since then, basically all computers have followed this basic design. So we won't get too much into the details of how these CPU chips are constructed, but it's important to be aware of some basic components, such as memory. You have a control unit, an arithmetic unit, and you have input and output. So here's another example of this structure. So the stored program computer architecture, generally the way it works, you would have instructions read from memory into a control unit, the data read from memory into a logic unit. You would perform whatever operation is listed in the instructions, and then you would output the result to some other input-output thing, right? And then you would proceed on to the next step. And here's an example of this if you're going to do this addition operation on two numbers A and B. So you load A, you load B, you load the instruction C equals A plus B, you store that, and then maybe you do this other operation, right? So it depends on, of course, the instructions depend on what exactly you want to do, but this is the basic overview of loading instructions, computing them, and then outputting the results. So modern processors are complicated. Don't worry about, we're not going to get into the details of this. As I said, just to point out that there are lots of different components of a modern processor that all do very different things to optimize computation. So the model that we're working with is going to be a much simplified model, but this is just to point out that when you look at it from a hardware perspective, things get much more complicated. So let's talk just momentarily about some advances in single chip processing that might be relevant to our discussions of parallel processing. So oftentimes these single chip processing advancements can be considered parallel processing, but are implemented at such a low level that programmers don't even notice them and are oftentimes just worked into the default serial coding that you might normally expect. So one example is pipelining, which is to split up a complex operation into simple components. So if you're multiplying a floating point number, FP there stands for floating point, you might do some operation where if you're thinking about the way that a floating point is represented in binary, you have there's certain terms for this. I can't remember off the top of my head, but the numbers that come before the decimal and the numbers that come after the decimal. And in order to multiply them, there's a way of breaking up those two operations and performing that multiplication and then combining them back so that you are able to parallelize that very low level operation. There's this idea of superscalar architecture, which gives instruction level parallelism on multiple functional units. So we talked previously about how a CPU might have multiple functional units, a functional unit being an arithmetic unit or a logic control unit. So having multiple functional units enables instruction level parallelism on a very low level. This is oftentimes something that's handled by the compiler and is invisible to the programmer, but it's important to be aware that it exists. Data parallelism. So this might be a technique that allows, in which special registers allow single instruction on a data array. So if you're multiplying two arrays, you only have one set of instructions, but you have a large number of pieces of data that you're operating on, which allows for that operation to then be parallelized. An example of this could be a GPU, in which you have a large number of components of a matrix that are in each time step, the same operations are being applied to every element of that data array. So this is an example of data parallelism at a low level in which this parallelization can occur. And there are some other types of advances that are not really parallel, but still good to be aware of. So out of order execution allows processors to split up tasks that are independent of one another, and provided that they are independent, this out of order execution can let certain processors move, just based on variations in hardware execution time. One processor might get to step 5 before the other processor gets to step 5. So they're allowed to do this out of order execution. Large caches, so this would be providing more memory to the chips, and reduced instruction sets. So this is something that was developed quite a long time ago now, but on a low level, having a very small amount of possible instructions actually allows for computations to be optimized at a very low level. So that's our advances in single chip processing, some of which represent parallel processing that is invisible to the programmer. Others represent just certain techniques or advancements in chips that allow single chips to be slightly more optimized. So certain advanced techniques on this regime can lead to complex behavior in practice. So what we're looking at here is an operation where you are multiplying elements of an array. A is equal to B times C. And because each processor is only able to complete one operation at a time, what happens is if you're using multiple processors, each processor can process one instruction at a time. So when you're starting, only one processor is active, but as the next step gets implemented in each clock cycle, you have this wind up time and wind down time that occurs at the beginning and the end of the process. So it's not like all of the parallel processes start at exactly the same time. There's this wind-up period in which the instructions are fed to processors, and then the wind-down period where the first processor that was fed the instruction completes first, and then the instructions sort of propagate backwards. And in practice, what this leads to is a certain type of optimization in which the number of processors and the number of steps in the program relates to this additional efficiency that you can see depending on the relative numbers of these things. So, basic idea of parallel computing. We had mentioned this previously. By construction, you need multiple processors to achieve parallelism. Can't do parallelism on a single processor. Although before we were talking about doing parallelism on a single chip, that chip is composed of multiple processors. So by construction, you need multiple processors to achieve parallelism. So this is an important image to keep in your mind. So parallel architecture, there's a few different ways of achieving parallelism. Modern CPUs are almost always parallel in their most basic construction, as we talked about. CPU, central processing unit, referring to it as hardware, i.e. some type of physical chip in the computer. As we'll see, terminology might have different meanings from a hardware perspective versus a programming perspective. That's something to keep in mind. Modern CPU chips have many individual processing units built into them. As programmers, we frequently only care about the number of processors, but not how they're constructed. So in some cases, it does matter. In other cases, it does. So it's just important to be aware of these things as we move forward. So here's a hardware perspective on parallel computer architecture. So what you see here, all of those P's there refer to a single processor. There's the L's there refer to different types of caches. We don't need to get into the detail. Again, just to demonstrate that when looking at the hardware of a parallel chip, there's oftentimes a lot more going on than we're really aware of as programmers. And the simplified programmer's model looks something more like this, where you have a processor that's attached to some type of cache memory that's attached to, I have the codes here, so M is the memory, and then the processors communicate with each other via some type of communication network or network interface. And in this example here, we're seeing that each chip physically only has one processor. As we mentioned, modern CPU chips oftentimes have multiple processors. So in reality, you have something more like a hybrid model in which each chip has multiple processors, and then they're connected to some type of shared memory. And then that shared memory and processors are connected via this communication network. So this is more so the model that we should be considering when we're thinking about processors in the HPC. So we're going to talk now about the different paradigms of parallel. So this is a model called Flynn's taxonomy, in which these 4 different regimes are described that allow different types of parallelism. So the first, SISD, refers to single instruction, single data. And this is the conventional serial computing. It is not parallel. It's included in here just for completion, but it's typically not parallel. SIMD on the top right there, that's single instruction, multiple data. So that, for example, can be related to processors such as vector processors, ones that have this superscalar architecture, or GPU processors, the most common example being a GPU processor. So single instruction, multiple data, when you're executing one set of instructions on a large array of numbers. MIMD, so the bottom right there, that's multiple instruction, multiple data. Of course, this requires multiple processors, and the majority of modern computing, especially in the HPC regime, falls into this category of multiple instruction and multiple data. And then the last one, MISD, not really regarded as a useful scheme. I'm sure there are certain cases where this is used, but they're very rare. They're sort of edge cases. In practice, this is not typically used, so we don't really need to worry about that one too much. So we have the three regimes of computing that we need to consider here: the serial computing of single instruction, single data, the specialized computing of SIMD, where you have a single instruction set but multiple data, and then the more generalizable scheme that falls under MIMD of multiple instruction and multiple data. So here's just a reminder of HPC parallelization. So you have serial versus shared memory versus distributed memory. We talked about this earlier. Just as a reminder really quickly, shared memory refers to single node computing where you have multiple CPUs, multiple cores that are able to access a shared memory space. Whereas distributed memory, you have multiple nodes that don't have a shared memory space, and these need to communicate with each other. So typically speaking, shared versus distributed memory does not necessarily specify whether a program is being executed as SIMD versus MIMD, right? Single instruction versus multiple instruction. Most parallelization on HPC is MIMD. SIMD typically is used in the GPU world. So if you're using GPUs, this could be considered SIMD. Most programs use shared memory parallelism by default. Distributed memory requires specialized software, as we talked before, to manage internode communication, usually some form of MPI. So that's important to remember if you're interested in scaling up your work to go from shared memory parallelism to distributed memory parallelism. This is not something that can be done just by requesting multiple nodes. If I have a program that works in shared memory and I try to run that on multiple nodes without adjusting my parallelization scheme, it's not going to work the way that I expect it to. So distributed memory oftentimes requires very specific implementation of internode communication protocol. The slide isn't loading. Okay, interesting. Anyway, so just to get more in detail with these different paradigms here, I think it was just one of these images that didn't load. So let's see if it shows up here. Yep, okay, that's not there. That's fine. So single instruction, multiple data, right? So all processing units execute the same instruction set in any given clock cycle. So you can see at that top image there, the instruction pool has a single arrow that is pointing to each of those processors. So that's the same instruction that's being fed into those processors. However, when you look at the data pool, each of those arrows is separate. So you have different pieces of data that is being fed into each processor, which then executes the same instruction. So, of course, this isn't going to be applicable to every single type of problem, but best for ones that have a high degree of regularity, such as graphics, image processing. Oftentimes, training machine learning algorithms can fall into this category as well. So, typically, this has synchronous or lockstep execution. So each processor executing the same instruction in the same time period. So that allows them to have a high degree of regularity, or, they actually match in each clock cycle. They're doing the same instructions, so they're able to stay in sync with each other. And this also allows for deterministic execution, where the result of a particular calculation is always going to be exactly the same. And we'll talk about non-deterministic execution shortly. So there are two different types of varieties of SIMD. You have processor arrays, and you also have vector pipelines. And of course, as always, these are topics that are very deep. They can get into a lot of different details, but this is just to show the bird's eye view here. So moving on to scaling, I guess now is what we're going to do. I thought I had a slide on MIMD. Yeah, it's right there. Got skipped for some reason. show anyway. Here we go. All right, multiple instruction, multiple data. Shame that these images aren't loading, but that's all right. So multiple instruction, each processor may be executing a different instruction stream. Multiple data, every processor may be working with a different data stream. So when you see here the list of processes, actually that was the one that was missing from the previous slide. It showed an array of processors, each with the exact same set of instructions. In this instance, you can now see that each of those processors is calling a different set of instructions. So you now have processors that might not be synchronous, right? So if the instruction set for processor 1 is different than the instruction set for processor 2, it might take processor 2 a different amount of time to complete. So this is what we mean by processors becoming out of sync. So it's good to point out here also that many MIMD architectures also include SIMD subcomponents, where a single instruction stream is fed into all of the processors on multiple data for a certain component of that process. Okay, so let's talk a little bit about scaling laws now. So we've talked about the different regimes of parallelism, and now we're going to talk about scaling. So scaling is when we're considering how do we change our number of processors, how do we change the size of our problem, and what types of speedups are we expecting to see based on those changes that we're making. So parallelization, typically, if I have a particular problem that I want to solve and I increase the number of processors, the idea here would be that the time to execution would decrease as I increase the number of processors. So that would be something called Amdahl's law or strong scaling. So how does increasing the CPU count decrease the time to the results? That would be the top graph there. So the speed up is the ratio of times to execution for a single processor versus the number of processors that you see on the x-axis. So ideal scaling would go as 1 over the number of processors. In practice, it doesn't always work like that. The other type of scaling, so we call this weak scaling, don't read too much into those terms. Oftentimes, weak scaling is a much more powerful type of scaling to consider. So Gustafsson was analyzing Amdahl's law and realized that in practice, what really happens is rather than keeping the problem size fixed and increasing the number of processors, the problem size oftentimes scales with the number of processors. So if I'm increasing my number of processors from 16 to 64, I might also be increasing the resolution of my simulation by a factor of 4. So the weak scaling asks, how much can I increase the problem size and CPU count for a fixed time to result, right? So let's look at these each in a little bit more detail. And just as a warning, there are some equations coming up. They won't be on the exam, I promise. There is no exam. So Amdahl's law, just to look at it in a little bit more detail here. So how does the time to completion vary as we change the number of processors n, as well as the fraction of code that is parallelized p? So p represents the fraction of execution that gets conducted in parallel. And in this case, we're also making some assumptions about there being no overhead, that there being no time taken in between communication with processors. So this is a very idealized version of this. In practice, it might not look quite so much as simple. So the speed up S as a function of both the number of processors and the fraction of code that's parallelized is given in this form. And the limit as n approaches infinity, so basically saying, what's the speed up if I use an infinite number of processors? And that would be the inverse of the fraction of code that is parallelized. So if I have code that is 0% parallelized, I substitute 0 in there for p, and the speed up is a factor of 1, which obviously isn't very good. It's 0, you're not getting any speed up from that. So if then 50% of my code is parallelized, then I can achieve a maximum speed up of 1/1/2, which is 2, right? And then you can kind of substitute different values there. And you can see on this graph, the speed up gained. So each of those lines represents a different fraction of the code that is parallelized. So of course you can get a much higher speed up from a much higher fraction of code that is parallelized. And then you do reach a sort of asymptote or a maximum achieved speed up based on the number of processors that you have. So this could be a good way of determining, okay, you know, I have my code, maybe half of it is parallelized, and then you can go look at that blue line there. Okay, so I really achieve maximal speed up at about 16. I might even be able to get away with using 8 processors, but this tells me that using 500 processors does nothing for me, right? So this is an important consideration to make based on the amount of code that is parallelized and the number of processors that should really be implemented in order to gain the maximal speed up from that particular piece of code. So this is useful. Here's another graph of the speed up versus the fraction of parallel code for a fixed number of processors. So you see that it reaches fraction of parallel code only makes sense to go between 0 and 1. So it's a little hard to read, but in there, the left and right ends of that should be 0 and 1. So it doesn't make sense to go beyond 1. So fraction of parallel code, you get a maximal speed up related to the number of processors that you have when you have 100% parallel code. And again, speed up being the amount of time to execution relative to a serialized version of that code. Okay, that's Amdahl's law. Continuing on now to Gustafson's law. Rather than assuming a fixed workload, we're going to now assume that the workload for the parallel portion of the task scales with the number of processors. So now the work that's being implemented is n times the parallel work that was before. And if you want to see a little bit more detail of the derivations and other explorations, I've included a link to a reference in the bottom there. But now we have this equation, which tells us that the scaling, the speed up here is achieved by this equation, which is now a linear equation. And of course, now we're assuming that the problem size is increasing as the number of processors is increasing. And comparing these scaling laws again, so strong scaling, Amdahl on the top there. The ideal scaling for this would be for the time to completion to decrease with the number of processors that are implemented. And the ideal scaling for Gustafson would be that the time to completion scales proportionally to, that the time to completion stays constant when the number of processors is increased because the amount of work that goes into those processors is also scaling with the number of processors. So hopefully that makes sense. And then we can see there also poor scaling would be for Amdahl if the time to completion decreases, but not maybe quite as fast as we expected it to. And then poor scaling in the case of Gustafson would be as I increase my number of processors and as I increase my problem size, that the time to completion actually starts to increase as that problem gets bigger. So hopefully this makes sense. If there are any questions, feel free to let me know. So those are the two main scaling laws that we need to think about when implementing parallelism. So it's important to recognize here that there are a few assumptions that go into these scaling laws that make them ideal. So in practice, parallel work may not be evenly distributed among processors. In practice, there's typically some type of interprocessor communication overhead in time. There might be some time taken to write data to the disk that is not accounted for here. And there might be some memory communication between different levels of memory on the hardware chip that is not taken into account here. So these faulty assumptions lead to less than ideal performance scaling in practice, but certain techniques can be implemented to partially mitigate these effects. So now we're going to move on and talk about these types of practices that we can use. So overhead. So if tasks are not completely independent, then processors will generally need to communicate with each other. And this image that you're seeing here is a variety of different types of interprocessor communication. So broadcast could mean I'm taking the output of this processor and then sending it to all of the other processors in my network, in my job, right? And then there's a handful of other different types. So in shared memory parallelism, this usually doesn't need to be explicitly invoked. This communication takes place on a much lower level. In distributed memory or multi-node parallelism, as we've talked about, communication protocols must be programmed explicitly at some level. So either this is something that you have to program into your code, or maybe it's something you're using a library which in which somebody else has already programmed that, but you can import that library. So things like, Python MPI for Pi can be used. So this crazy looking image here is an example of communications overhead. So this is a process call graph from a parallel execution of Hello World. And most of the routines being called here are being called from communication libraries. So this is, you can see on the left there's a little bit of MPI code. It's a little grainy, but you can still kind of see what it's saying there. So all of these communication calls are from MPI. So overhead is a real thing to consider when analyzing the performance of your parallel codes in a multi-node context. Load balancing is another thing to consider. This effectively means, when you considering the ideal case of parallelization, you would imagine all of your processors have the exact same amount of work to do and that they'll all complete in the same amount of time. In practice, this is quite difficult to achieve with the MIMD parallelism. So some tasks may have more work to complete. An example could be astro simulations. This is my background. Some regions are much denser than others. So you can see in the middle of this graph, there's a lot more going on, whereas regions towards the outside have a lot less going on. So if I were to take this simulation space and just break it up into even chunks and feed each of those chunks into a processor, the processors that get assigned chunks near the middle are going to have a lot more work to do than the chunks that are towards the end. This is just one particular example of this. This also can be applied to other types of software like climate modeling or sparse matrix multiplication, things like this, where the work is concentrated in one particular area, but may have large regions where not much is happening. So techniques such as adaptive mesh refinement can be implemented to improve load balancing here. So rather than dividing up the work evenly in space, you try to divide up space so that each segment of that space has more or less the same amount of work. So you can see here in regions of higher density, those regions of space are much smaller so that each processor that gets assigned to that region has less to do. And then here on the left is a visual demonstration of load balancing, load imbalancing. You see that some tasks finish their work much earlier, and then they have to wait until other tasks get completed in order for them to then get assigned their next task. So any downtime, anytime that a processor is not working on a task, is room to be improved. There's efficiency that can be gained back there when you're thinking about optimizing your code. So in some techniques that people use to optimize their code, similar to adaptive mesh refinement, you have this idea of domain decomposition. So you're breaking down your data set into components and then running a parallel task on each of those components. So you can see a couple of different images here of breaking down your data set. So domain here refers to breaking down the data specifically. So you have each task that's being run on a different component of that data. That's why it's similar to single instruction, multiple data. So when you're implementing this technique, you might be considering a single instruction stream. You might not be considering a single instruction stream. But the idea here is breaking down the problem, sorry, not the problem itself, but the data that the problem is operating on into multiple components, and then running a different task for each component. And they're, depending on the dimensionality of your data set, there can be different ways of decomposing that data set into different processes. So you can see on the right there, if I have two-dimensional data and I'm feeding it into 4 processors, there's a number of different ways that that domain can be broken down into components that get then fed into each processor. And this probably would depend on the type of task that you're running. Functional decomposition is similar to domain decomposition, but domain decomposition is operating on the data itself, whereas functional decomposition is operating on the instruction level. So the idea here, you can see this image, you have your problem instruction set, and then you are taking that instruction set and then breaking it down into components that make sense together and feeding those components into different parallel tasks. And you can see sometimes, you know, looking at that kind of bluish purplish region, there are some instruction sets that might make sense to go together into a parallel task that might not actually be executed near each other inside of the original problem instruction set. So, and this can be implemented at multiple levels. So you can implement this at the program level. You know, I can have one Python script that performs one set of instructions and another Python script that performs another set of instructions, and then run them as separate jobs on the HPC. I could also have within a particular program multiple functions that perform different tasks, and then, you know, I could even break that down even further to say within a particular function, the parallelization can be applied to different operations inside of that function. So you can get as granular as you like with this. You can also get as broad as you like with this. It's just a technique of breaking down instructions into different sections, oftentimes depending on their need. So asynchronous computation, let's talk about this momentarily. So latency from interprocessor message passing, minor variations in completion time between parallel tasks, and other subtle timing effects can cause computations to be performed in different orders on subsequent runs. So, you know, I run my program once and then I run my program again. And if I look at the order of the computations, they might be slightly different. So if computations are independent, there's not a problem here. But if the computations rely on outputs of other computations, for example, if you're computing nearest neighbor physics, then this can lead to codes that are non-determinate. So we talked about deterministic code execution briefly before. Here's an example of a situation that can produce non-determinate codes. Parallel execution can lead to asynchronous computations and then indeterminate codes depending on what's exactly being implemented. Here's an example of this happening. So what happened in this example was you have this region and there are these little balls that are then fed into this region. They're sort of being like shot out of a cannon. And what happened was the programmer ran the simulation, found the position of each of those balls, color-coded them to make this image of the chicken, and then reran the simulation. On the left, you see the simulation being reran under serial, meaning that this it was a deterministic execution that was able to recreate the image of the chicken. And then on the right-hand side, you see a version of the code that was rerun in parallel, which then distorted that image of the chicken because of the non-deterministic execution. And this is a physics engine that this person demonstrated. So I highly recommend looking at this video if you want to learn more about coding in parallel, because he walks you through writing a physics engine from scratch, as you can see from the title of the video. So if that's something you want to get into, it's a great resource. And here you can see a great example of non-deterministic code execution. Meta-parallelism, don't Google this. This is just a term that I made up. Techniques that exist above the level of an individual program that enable users to take better advantage of HPC resources to either run a fixed amount of work faster or to run a larger amount of work. So some examples could be using array jobs to run 10 simultaneous programs rather than running each of those programs one at a time in order. You could decompose a program or an analysis pipeline into segments based on resource usage. So for example, if I have two portions, A and B, of a program, and portion A requires very high memory usage, while portion B requires very high CPU usage, it might make sense for me to break that program into two separate jobs, run portion A on a high memory node, and then run portion B on a standard node. So this is a way of optimizing your workload to the different types of nodes that are available on the HPC. Practical examples provided next week. And we're pretty much out of time here. So, and these parallel algorithms I included mostly as a demonstration. So I'll just show you a couple of things real quick, and then we'll call it for the day. But I'll hang on for a couple of minutes just in case there are any questions. So computations can be represented by graphs. The one on the left here represents a serial computation of a sum of 8 numbers, and the tree graph on the right represents the same sum, but computed in a way that is more suited to parallel implementation. Here's an example graph for matrix multiplication, where you can use multiple processors to compute the result of your matrix multiplication. And there are also much more advanced techniques, such as using processor hypercubes, but we're not going to get into that. And if you feel adventurous, this is a cool problem that I stumbled across online. The Mandelbrot set is a famous fractal defined by this equation. There are plenty of resources on the Mandelbrot set. If you're not familiar with it, there's plenty of resources there, Wikipedia, as well as I think that first link goes to Wolfram Alpha. So good stuff in there. If you'd like to try to think about how to implement calculating the Mandelbrot set, both in a serial way as well as in a parallelized way. And then maybe we'll think about how we can actually implement that with some code in Python next week. And here are a few additional reference links that you might be interested in checking out. And that's it for today. So thank you for listening.
Pseudo code. What does that mean?